all got my message. So we are ready to rock and roll here. You know how easy I am distracted, so you can imagine I'm a little bit more than usual. Here we go. We were looking at the area between two curves, which is this. And what you can see here is the generic form that you do when the functions are in terms of x. And if you want to find the area between two curves, there's another version that looks something essentially like that. And the normal way to do this would be something like this. You get the question, and step one is that you'd use Desmos to draw both sketches. Now, step one doesn't always happen because some of the questions already give you the sketch, in which case that's great. Then you move on to step two. And step two is you find the limits of integration. Which are basically, what value of x do you start and finish at? Or if it's the other orientation, what values of c and d, the values in y that you start off? And the order of subtraction. Now, you know you're going to have two functions, right? One of them's x cubed, the other's 2 sine x. One of them's y squared plus 1, the other's 4 minus y squared. One of those goes here first. Then you take away, the other one goes second. If you do that, then you are set up with an integral, which takes us to step 3. Integrate. Now, what can happen in integration? Sometimes you get really lucky. You just use the power rule. But don't you also sometimes have to do U-subs, substitution? And sometimes you have to use this guy. Sometimes you have to use standard integrals. So that's kind of our shopping list. So what I thought I'd do is we'd go and I'd look at some questions and set up kind of that process. So the one I just happened to be looking at is question 1. You know, it's quite early on, but it's a little bit. You've got this guy. And you've got that guy. And we're being asked to sketch the region, and they give you 4 choices, and then find the area between them. So I'll try my steps now, see how good I get at that. Okay, so here goes. Right, now I've got Desmos. Going to go over here and type in y equals 13. Subtract x squared. And it's not really seeable, but that's fine, we'll fix it. And then the second one is going to be x squared minus 5. There's a little thing down here that looks like a keyboard. And if you click on it, you get x, like that, or y. In this case, I want y equals. So you could do y equals x squared. And then you can do subtract 5. That's just a different way of doing it. Right, so I've got both curves. I can't really see what's going on at the top, and a little bit at the bottom is missing there. I can see it now. If you've got a mouse pointer like mine, it's got a little wheel in the center. What you can do is you can move it like that. Now, can you see the picture of the two curves? The red one going like this, that's the first curve, and the second curve is going like that. Not only that, if I put my mouse pointer on it, can you see that guy's at -3 and this guy here is at 3? Now, one of the pictures that we have in the homework, which I believe, let me find it. One of the guys that you have in the homework, boom, looks a bit like that guy. You see him? So we want one that goes down to -5. So I pick that one. So what the homework does is it gives you 4 graphs and you pick the one that looks like ours. So I'll now return back to the whiteboard and kind of improvise a little bit. Our guy, the guy we just had a few minutes ago, had a fella that went like this, and another fella that went like that. And there was a point here and here. Can you remember what the number was for those guys? Can you remember the x coordinate of these two fellas?
-3 and 3.
Thank you, because I wasn't sure. So we got that. Now, one of these curves was that shape, the other is this shape. The area that they're asking us to find is this little area in here. So if I'm looking at it top to bottom, there's my little rectangular strip that I like. This curve here, the one that's sloping like a tunnel, a cave entrance, that one goes like that, and that one was 13 take away x squared. And the other one, the one that looks like this, that was the x squared minus 5 fella. So I can now put all this information that I can see here, which I got from Desmos, and I can use it to find the area between the two curves. It's going to be the integral from -3 to 3 of the top curve, which is 13 take away x squared, subtract the bottom curve, which is x squared minus 5 dx. I'll pause for a minute. Can you imagine putting that guy in Desmos so it's easy to see, right? That picture allows us to tell that it crosses at -3 and 3, so that's where these came from. This Desmos told us that the high up one was 13 minus x squared, and the lower down one was x squared minus f minus 5. So that's basically the f of x and the g of x that I need. Now, I'm just going to do a little bit of tidying up. Essentially collecting like terms. Are we good at that point? So this thing in Desmos was essentially my step 1. Setting this up was essentially my step 2. Now I'm about to integrate that and eventually get a number, and that's essentially step 3. Right, so picture, get your information. set up your integral, make it look as pretty as possible. That's step 2. And then evaluate that integral. Right, power rule, 18, 18x. Add 1 to the power, divide by the new power. Evaluate at -3 and to +3. That gets me 18 times 3, take away 2/3, 3 cubed, minus 18 times -3, take away 2/3, -3 cubed. That's what calculators are for. Getting deja vu on this one, but they all look the same to me after a while. This guy here gets you 9, that gets you 18. Gets you -54. This guy gets you +18. So we get 54, take away 18, add a 54, take away an 18, which is 108, take away 36. And it came out as a really nice answer. Do not expect really nice answers in all of these questions. I was doing one at the start of today and it came up some, God, ridiculous answers that now I'm looking at it, I know it can't be right. Weird fractions everywhere. So that, to me, although it's pretty messy, was actually at least a nice answer. So that's step 3. Actually, step 3 starts about here. Okay, shall I try another one? Are we fed up with these, or do you want to see some more? You want to see another one? Okay.
We'll do one more.
Sure. Anybody got any particular preference, or shall we just scan through them and look at them? That's an idea. Why don't I? He thinks to himself. Right. That was the version of question 1 I just did. Question 2 already has the picture set up for you. So I'll talk through that one. That's not the one I'm going to do. Do you see that the x value starts at 0 and it finishes at 1? So it'll be the integral, imagine an integral sign here, from 0 to 1. If you do one of my little vertical rectangle things, can you see that 7e to the x goes first? Take away that guy. So you're going to do 7e to the x minus 7x e to the x squared. So that would be the final answer. Right. Here's question 3, where you've got the 2 pictures and they like my little rectangle. It's an x squared minus 3x and it's a y equals 3x. I would still do that in Desmos. Why? Well, you don't know which one of these 4 pictures is the right answer until you see what Desmos looks like. Secondly, Desmos will allow you to get the x coordinates of these points. Although you could have a fair guess in this picture, I think it's better if you can be sure. But if you want me to do that one, I will. Here's a y equals cube root and a 1 over x kind of guy. Again, the picture's drawn with the information given. We could do that one. And here's one with a cosine, which is one I think I'm going to do now. 9 cosine pi x and 8x squared minus 2. Right, that's a pretty ugly one. I think I should do that. Are we good? Let's do that one. Now I'm just going to write down the key information. And the curves I'm going to be doing are 9 cosine pi x. And the other curve is going to be 8x squared take away 2. Okay, can you see Desmos? Because I may have to go in and out. Okay, so I'm going to cancel these 2 guys out, and my new question is 9 cosine pi x. So y equals 9 cosine, What did that look like? I hit a P by mistake. 9 cosine, do a bracket. If you hit this key, you'll be able to find the pi button somewhere. There it is. Pi x. So that's the first equation. Ooh, that looks weird. The second equation is going to be y equals 8x squared take away 2. Right, if I scroll inwards, now I can only do so much before it becomes messy. So I'm going to go to the little graph setting, and it looks to me that if I do -1 to 1 on the x's, I'll probably get everything I need and that I want, I'll be able to see in that range. So -1 to 1. I think I nailed it. Can you see the shape you want is this? Looks like some weird hat, right? This area in here. Also, do you see that this number here is -0.5?
Yes.
Which is -0.5, and the other one's +0.5. And then I have a second curve that looks something like this, and that second curve happens to be the green one, so that's y equals 9 cosine of pi x. And the blue one is 8x squared. So what Desmos has allowed me to do, if I now return to my whiteboard, is that's essentially the bit we're trying to find the area of, right? This here. Desmos has got all the information ready to go. So here goes. The area is going to be from x equals -0.5 to +0.5. The guy on top is this fella. So it's 9 cosine of pi x. Take away this fella, the x. So we pretty much taken care of, put my little steps here. Use Desmos, done. Find the limits of integration in the order of subtraction, done. Now we're going to move on to step 3, integrate. That kind of depends on what you've got, how you approach it. I'm going to do something that I typically wouldn't do, but in this question, I think it's helpful. You are allowed to take an integral and split it into 2 separate integrals, and it's the same answer. It kind of makes sense, right? That, take away that. Find this integral, take away, find that integral. Now, the reason why I want to split these is because the techniques I'm going to use are quite different. On this one here, the -0.5 to half, 8x squared take away 2 guy. Can you see that I can just simply use the power rule and get the answer? On the other hand, 9 cosine pi x. What technique do you think I'm going to use to integrate 9 cosine pi x?
U sub.
Yeah. So we'll hold that thought until a little while from now, and we'll do a U sub on this. Let's get this guy out of the way. Power rule. Add 1 to the power. Get this fella. Evaluated at -1/2 and +1/2. That will get you 8/3 1/2 cubed. Take away 2/3 times 1/2. Subtract. Plug in -1/2 now. 8/3 -1/2 cubed. Take away 2 lots of -1/2. That guy there gets you 1/3. Take away 1. This guy here gets you -1/3. Some's not right. Oh, totally okay. I was about to say something's not right because that's a negative number. And I was thinking the entire answer, and I know it can't be negative, but this is okay to be negative because it's just going to be this bit. So what do I get? I get 2/3, negative 2/3, take away 2/3. The answer is negative 4/3. So this guy in here is him. So that's okay. Because that's going to get me that one unfinished. Now the other fella, the first one, I'm also going to do him on his own. And someone's already said to us, a U sub. So I guess my next question is, what U sub? What U sub would you use in this question?
IX.
Correct. And du by dx then is just pi. The crossover gives me this. And when you divide both sides by pi, you isolate the dx to get that. And this integral now becomes 9 cosine u times 1 over pi du, which becomes 9 over pi cosine u du. You then integrate. If you integrate a cosine, you get a positive sign. You then return the u back to pi x, and at this point, you then evaluate the integral at plus and minus a half. So although I did the u sub to get to here, that's only so I can return it to this, the x's, and then use the limits of integration. So that's going to be 9 over pi, the sine of a half pi, take away 9 over pi, the sine of negative a half pi. The sine of a half pi is 1, so that's 9 pi times 1. This one's a bit trickier. What's the sine of negative a half pi? What number is it? It's also got a sign attached there. What's sine of negative a half pi equal to?
-1.
It is. You know, you could put that into Desmos and just look at it and you could check it was. Which means I now have 18 over pi when you add, because this two subtractions make it an add. 9 over pi plus 9 over pi is 18 over pi. I have 18 over pi. And the final answer, as weird as it looks, is just that, because we want exact values. So that means that we only take, we don't turn anything into a decimal. And that can mean, as it does here, that you end up with an answer having 2 pieces to it. I could even imagine an answer with, a square root of 7 plus 4, minus root 3 or something, right? Whatever you get is the answer, even if it looks kind of messy as it does here. Is there any question about that, or do you feel a little bit more comfortable with how we would do a situation like this? Okay.
I think I'm getting it.
Okay, it's one of those things. It's the more you do them, the easier it becomes. It's not that they're ever going to be easy, but they do become easier, right? And so what I'm looking at now is really the second situation. And the good news for me, I think, the good news is that there's a lot of transfer. You kind of do almost exactly the same thing, But in this world, you have a curve that's called x equals f of y, and you have another curve, and it goes whatever way it goes, and it's called x equals g of y. And we are interested in the area between the curves, which is all this. And I'll call this value of yc and this end value of yd. And if you want to know the area between the two curves, it's the integral from c to d. Now, you don't have a top and bottom, right? What you have instead is a right and left. So the one that's furthest to the right, take away the one after that, right? The way I look at it is, you might think, well, why should that one be first and take that one second? Any point on this curve, won't its x values be bigger than any point on that curve? So the biggest x's belong to these, take away the smaller x's. Aren't the biggest y values on the top curve, and the biggest and the smaller ones are on the bottom? Top, bottom, right, left. So everything that we've done, all my 3 steps, we do it as well. We're going to use Desmos to draw that damn thing if we need to. We're then going to find the limits of integration, in this case the C and the D, and who goes first and who goes second, so we can set this up. And then step 3, we are going to integrate. And the only difference is that we're going to integrate y. So it means that your answer might be, y cubed take away 2y that you integrate. It's the same process, right? You use power rules, you use u subs, you use standard integrals to get the numerical answer, and you're finished. Okay, so let me see if I can find one now. You can never find one when you want one. Here's one. Question 13. Question 13 already has the picture, so we don't really need to do so much. We have a guy that looks like this. We have another curve that looks like this. This one is called e to the y. This one here is x equals y squared minus 6. And we're being told to do it from -1, which is here, to +1 that's here. So the area that we're being asked to find is from -1 to 1 and the area between these two curves. So my step 1 wasn't necessary in this question because it's already there. So I can move on to setting up the integral. -1 to 1. Now, one of these guys, either e to the y or y squared minus 6, goes here. And then the other one, next door. In my very crudely drawn picture, which one of these two, the e to the y or the y squared minus 6, should go first?
E to the y.
Great. Then you take away a y squared subtract 6. And that's step 2 done. Set up the integral with the limits of integration. Now what I'm going to do here is really just some tidying up. This particular question, I do not need to break into pieces and do each piece. This one is relatively straightforward to integrate. This fella gets you e to the y, power rule on this fella, and 6y. Integrate e to the y, e to the y. Add 1 to the power, divide by the new power, 6y. And let's plug in 1. You get e to the 1, 1/3, 1 cubed, plus 6. Take away e to the -1. -1/3, -1 cubed is a bit messy. And that guy's -6. So this is e. And this combined. And what do you get? 18/3, 6 3s is 18. Take away, so 17/3. This guy is essentially 1 over e. This is messy because that's -1, so that's a plus. Plus with that gets me -17/3. So I have an e 17/3. Take away that guy, add another 17/3, and the answer is an ugly combination of those three things. So the area between these two curves is that number there. Any questions about that one, or are we good? We're good?
I forget, how come the e to the y goes before? Or does it matter?
How come this goes, how does this come here, or is it down here you're talking about, Skylar?
Yeah, I thought you were, when we first started, I
Where's
thought you said e to the y comes first, or I wasn't quite sure.
It did, it's here. So how do I know it's first? If you're doing it in the orientation where the y's are involved, the one that's furthest to the right goes first. And the other one goes second. So e to the y goes first, because that's this curve, it's e to the y. Take away, this guy goes second. So that's how I knew to do e to the y first.
Thank you.
Okay, I'm going to move. We're fine. I'm going to move then. Still a little bit more to do in these guys, but I think we just need more practice. So this one here is going to be question 14, or like it. We have x equals 7y squared, and we have x equals 4 plus 6y squared. Okay, x equals 7y squared, x equals 4 plus 6y squared. And we are being asked to find the area enclosed by these, right? The area between those two curves. So that pretty much means I'm going to do every single one of the three steps. So I'm going to be starting with Desmos. And I'll show you what that looks like. The first curve was called x equals 7y squared. And the next curve is going to be called x equals 4 plus 6y squared. And I can't see those. Oh, there we are. Okay. They're over here with a horrible scale. So let's go back in and play about with some scales. It's obvious that the y values are huge, and I don't want them to be that huge. So I'm going to reduce these guys to 5 and -5. and see how that helps. Okay, let's have a look. That's a bit better. It looks like I probably don't need quite as much as that. It looks like they intersect as well, so I'm going to go back to this window. A bit surprised by what the shape looks like, but that's fine. Okay, so I'm going to go here, and I'm going to make this guy -2. I'm going to make this guy 2, and hopefully I'll be able to see the darn thing. Okay. Something not right here. I know that the places where it should cross are 2 and -2, yet for some reason I'm not getting that. When I look at this picture, they're both happy faces and they seem to be crossing some hard to imagine point. That cannot be right. Okay, let me show you how I don't know why, maybe I'm just screwing things up today, why I'm not getting what I was expecting. You know that you can use Desmos to find out where they cross, and it should be nice and easy. But you can also find out where they cross by setting the equations equal to each other. Oh, darn it, they are the same. Okay, here goes. Subtract 6y squares from both sides. Do you see that the y values are plus or -2? So I know the integral is from -2 to 2. The reason why that graph was so ugly is at x equals 2, can you see the, y equals 2, can you see that the x coordinate is 28? So it actually was accurate. You know, the picture looked like this. And these numbers were 2 and -2, but this guy here was 28, right? Ridiculously big number. And I didn't even need those. So one of these guys is further to the right than the other one. And I'm not going to go back to the picture because it takes too much, but can you trust me, it's the red one, right? So the one that's furthest to the right is this one, and it's red, and the red one is 4 plus 6y squared. And the other one is that guy. So the limits of integration are -2 to 2. Furthest to the right, take away the other one. And combine these. Okay, from what started off as the ugliest looking question has actually become one of the nicest integrals. The guy on the right, take away the guy on the left, from -2 to 2, and I know that because of the little algebra I did here. This simplifies down. I can then do power rule. Plug in 2, 4 lots of 2, take away 1 cubed, subtract 4 lots of -2, take away that guy. You get 8, take away 8/3, and you get -8, add 8/3. What does that get me? It gets me 8 and 8 is 16, and -8, take away that, take away 16/3. 48, take away that guy. I believe the answer, you can check it later, is 32/3. So the process of finding the area between two curves where the two functions are given in terms of functions of y, like y cubes and y squares and so on, is very similar. Use Desmos if you need to get a sketch. Find the limits of integration, -2 to 2. Figure out which one of the two curves goes first, take away the other one, integrate, finished. The problem I was having with why I couldn't make this thing work is, I guess I should return and kind of visually show you why I was getting all combobulated. When you look at this question, isn't it very hard to tell that these two things cross about here? Yeah. See it at 28,2. The 2 is the y coordinate, and that's what I needed to know. But it just kind of blended into nothingness, and I couldn't figure out what the heck was going on. And so, there we go. It crosses at 2 and -2. Anything about that guy that we need to talk about? Okay. There's a third situation which works in both the x and the y direction. And that third situation is when the two curves cross over. So I want you to imagine that you've got a curve called y equals f of x. You've got your second curve y equals g of x. And you are interested in the area from A to B. So you're basically interested in these. The area tends to look like some weird pairs of glasses, right? There is a distinct crossover at this point here, which we'll call C again, to remind you. To find the area of this one, you split the problem into two pieces.
I'm still saying Desmos. I don't know if we're doing any problem.
Okay, thank you. Let me get into that. Right, so you get a crossover question. Right? You're trying to find this area, and because they change who's on top and who's on bottom, that's what I mean by crossover, you split it into two pieces. From here to here, from A to C, the red guy's on top, and the green one is on bottom. So that'll be the order. And then from C to the end B, the green guy's on top, and the red guy's on the bottom. So essentially what you do is that you subtract them, but you notice that you switch places. So for the first half, it'll be like A take away B, and then the second half, it's like B take away A. So in a question that involves a crossover, we need to just add a little bit extra work to the problem, right? So let me find a crossover question. I'll do one in the X's and one in the Y's. They're not as common. So actually, I'll do two in the X's and two in the Y's. That seems a little bit more realistic. Do we have an X and Y crossover I want to do? Okay. Looks like the only ones I can find are trig, and that was going to be one of my answers, but it looks like it's going to be both my answers then. So this is question like 11. We have a y equals 8 times the cosine is 7x, and we have a y that's 8 take away 8 times the cosine is 7x, and we're being asked to do it from here to here. Okay. From 0 to pi upon 7. So I need to get a version of that guy. I'm just clearing off Desmos right now. And I'm going to go in. We're going to see if we can sketch those two guys. So the first one is going to be y equals 8 cosine of 7x. I have no idea what I just did there. I don't have an awful lot of room on my table, doesn't help. Right. Ooh. Well, we'll fix that in a minute. Let's do a window. And the x-axis is going to go from 0. Oops. The x-axis is going to be from 0 to pi upon 7, because that was in the question. So there's my pi divided by 7. Right, that should make my window a little bit cleaner, right? Not like dead up to a point. I think I should look at what the y values look like. And I'm going to try -20. To +20. There. That's much better, right? That's what 8 cosine 7x looks like with a window that we can use. And I might have to tweak it in a minute. And the next guy is going to be equals 8 take away 8 cosines 7x. Hey, perfect. Can you see a crossover? Green on top, blue below, blue on top, green below. And can you see that guy there? The crossover is at what? Pi over 21. Can you see that pi over 21 guy?
Yes.
Okay, so I can tell you then that I'm going to draw a little baby picture of what's going on here. It looks a bit like this. And the green one, I guess I should make it green now. The green one, which is this one here, is 8 cosine 7x. And the other one is 8 take away 8 cosine 7x. Okay, so now I can forget about Desmos because everything I need is in my little sketch, which is this one. This one. Right, that's my miniature version of what we have here. So I need this guy, I'm going to call it A. I'm going to get this guy, I'm going to call it B. So the area between these curves is basically A plus B. A is the integral from 0 to pi over 21. Green guy first. Take away blue fill in next. Plus, starting at pi over 21 and finishing, that says 21 by the way, and finishing at pi over 7. blue guy on top, take away green guy on bottom. So can you see it's one take away the other and then they switch places? That's typically what's going to happen. Those two integrals are quite long, so let's see if I can tidy them up a little bit. From 0 to pi over 21, this guy, take away that guy, is going to be 16 cosines of 7x, take away 8. And then this one, which is from pi over 21 to pi over 7, is going to be 8 take away 16 cosines 7x. Now each one of them we'll find separately and then add the two answers together and we are finished. I'm just going to pick this one. Do you know if you can do this integral? Can't you do that one? I mean, it's very similar looking. So let's see what this one looks like. Oh, I may have to do this at the side. This isn't hard to do. And the reason I want to do it separate is, do you notice that this guy needs another U sub? And you can't really do U subs when there's other stuff involved that has nothing to do with the U sub. It just clutters up the whole thing. So basically I said to heck with it, I'm just going to find what that A is on its own. And now I can focus on this fella. What U sub would I use for 16 cosine of 7x? I need a U sub for this fella.
Seven X.
Yeah. Didn't we do one earlier today that the same kind of thing happened? So it's the same kind of sub. If I'd planned ahead, I would have gave myself more room, so I'm just going to have to squeeze it up here. That's my U sub. With respect to x, that gets me 7dx, and so when you isolate the dx, you get that. So it's going to be the integral of 16 cosine of u's times 1 over 7 du. It's going to be 16/17 cosine of u's. That's going to be 16/7 the sine of u. You integrate a cosine, you get sine. That was going to be 16/7 the sine of 7x. And now I can evaluate it at 0 and pi over 21. It's going to get me 7 lots of pi over 21. Take away 7 nothings is nothing, which makes that nothing. All the time, I've still got this guy at the end. He's still there. Right, this fella here is 16/7. The sine is 7/21, which is pi over 3. I need to know the exact value of the sine of pi upon 3. Anyone know the exact value of the sine of pi upon 3? Last chance. Exact value, sine of pi upon 3 is root 3 upon 2. Take away nothing, take away that guy. And that guy cancels a little bit. So after all that work, I get 8/7 root 3, take away 8/3 pi. That's what that is. Plus, can you imagine going through the same kind of process but with this fella? It'll look very similar to this, and you'll get another answer. It won't be quite the same numbers, and the reason for that is that the limits of integration are slightly different. So don't expect that answer again, or even the reverse of that answer, but they'll be similar, that I would expect. And then whatever that is, you put them together, and you're finished. Okay, so you can hopefully plug away at that. I can imagine that there are lots of little places where you could lose a sign or not get an exact value. So you have to be extra careful. I guess I should leave that for a second. Are we, well, I don't know if good's a good word. Did we follow the process, even if you don't understand it all? But you can look back at this video and hopefully go through the steps one at a time and say, okay, what did he do to get this step? How did he get from 3 to step 4? And so on as he went through the work. I'm going to have to move this fella now. So we're looking at crossover questions now. So let's see what I have to try for my next one. Try to find another crossover. I'm scanning through. Done that one. Oh, here we go. Question 10. It's y equals the tan of 9x. Y equals 2 times the sine of 9x. And we're going to be doing it from negative pi over 27 to positive pi over 27. That is going to be a real long question, I can tell you right now. So what I'm going to do instead is I'm just going to show you bits of that question. And then I'm going to turn this guy, the whole question, into a PDF. And I'll just put it online, and that way you can read through the lines, because there's just so much of this that is going to cause trouble. So the first part I will do, which is we need to know what the heck this looks like, so I can get the crossover point, and I can then do the 2 separate integrals, who's on top, who's on bottom. So we'll take you to that part, and I'll tell you a little bit about how you deal with integrating the tan of 9x, and then I'll kind of leave it hanging like that, and I'll put the PDF up on the finish. So keep that guy, hold that thought, and we're going to do Desmos. Now I'm going to go here, and I'm immediately going to go to here, and I'm not going to make the same mistake I made last time. I'm going to make the x's negative pi divided by 27. And the other x value is going to be pi over positive 27. Now I'm going to go and type in the first function, which is the tan of 9x. Okay, It looks to me like I may have to fix the y values, but that I can do in a minute. And the next guy is going to be, what happened to my y's? Doesn't change the question, it just looks prettier. There we go. And then y equals 2 sine x. And would you agree that the y values are not very helpful? So I'm going to go in here, and it looks to me like I don't need to be any bigger than 2. So I'm going to go here, and I'm going to make the y values -3 and +3. And we are pretty much good to go. Can you see that from here to here, the blue guy is higher up than the black, and then at 0, the switch happens. You see it's black guy on top, blue guy on the bottom. So I do have a crossover. And so I'm going to write that down, and it's going to be the integral from -π/27 to 0. So that's going to be from here, that's where -π/27 is, to 0. And in this case, the blue goes first, and the blue is 2 sine 2x. And the black one, the tan of 9x, goes second. And then I'll do from 0 to π/27, which is this piece, and the black guy goes in first, so that's the tan of 9x. Take away the blue guy, the sine of 2x, dx. So from that picture, I got the crossover point, which is 0. I got who goes first, who goes second, right? High and low, high and low. And now I'm ready to move to the next phase. That was the guy that was on the left. That's the guy on the right. And I'm going to integrate these fellas, except I would do them separately. So this one here, oops, that's not right. We'd go -π/27 to 0 of 2 sine 2x dx. Take away -π/27 to 0 of the tan of 9x. And that would just take care of this one. And then you do the same thing over here, split them into 2. Now I need to find that guy. And I also need to find that guy. What method am I going to use to find the integral of 2 sine 2x? Two sine 2x. Yes. Are we getting used to this particular u sub world? It's actually quite a nice u sub, isn't it? Just 2x. That would get me 2. That would in turn get me that guy. And a little bit of crunching, but there we go. So it's going to be the integral of 2 times the sine of u, 1/2 du, and it becomes the integral of sine u du, and then off you go and you finish it, right? Now what about this fella? What u sub do you think you're going to use for the tan of 9x? It should be getting easier.
The 9x.
Right. And then you're going to pause, or you should, and say, wait a minute. There isn't any tan x here. But I'm going to be integrating it, I need to know what it is. Well, let's just take it a little bit further and show you what happens. Differentiate with x, you get 9. There's your crossover, and then you isolate. So this becomes the tan of u du. Oh, 1/9 du. So I need to integrate that guy. I need to find the integral of tan u. The 9th isn't a problem. That just makes it 1/9. And this is kind of clever. And the first time you see it, it might look a little bit out, but hopefully you'll agree that it's kind of clever when you see it. There is nothing in my list here that's going to help me. So it's not a standard integral. And it's on its own, so it looks like there's not a lot I can do with rewriting it, but I can rewrite it. What is another way of writing the tangent of u that you hopefully remember from trig? Tan u is equal to somebody over somebody else. Tan u is something divided by something.
Is it sine over cosine?
Yes, it is. And you might say, oh, well, how is that going to help me? Well, I'm going to have to change the name. It's not going to be called a U sub. I'm going to have to call it, what letter in the alphabet do you want? A W sub? Let's do a W sub. Make W the cosine of U. Then dW by du is negative sine of U. dW is negative sine of U du. And when you isolate it, you got that. So sine U over cosine U du becomes U sine U negative 1 over sine U dW. I shouldn't have called that U, should have called that W. Remember, it's W. And they cancel, and you get that. That is a log. That becomes that guy. So I now know that the integral of tan u is negative the log of u. And in case we forgot, wasn't u 9x? So we are going to be doing the integral of 1/9. Oops, already done that part. 1/9 a negative log of 9x evaluated at negative pi over 27 and 0. So I'm going to see if I can squeeze this guy in somewhere. Here. Tan x is negative the natural log of cosine x. So once you find a guy that you've never found before, and you think he might be something that's going to pop up again sometime, couldn't you just go to this list here and add him? Couldn't I put in a cotangent x if I wanted to? Maybe do a secant x, maybe do some other ones that I haven't found. And I could add them to my standard integrals, which means when I need to, I just come over here and I use it. And that is a massive question, but at least hopefully I've given you a good enough head start. And I'll do the completed version as a PDF for you so that you can go through it slowly when you come to do that question. And we need a joke because we've been working too hard and our brain is hurting. So I'm going to tell you one of my favourites. I've quite a few favourites about the Scotsman, the American and the Englishman go into a bar and they buy a pint of beer and 3 flies come in and one lands on each of their pints of beer. So far, so good. And what happens is that the Englishman's looking at his pint of beer and he sees this little fly swimming about in it and he goes, "Oh, that's disgusting," and he throws the whole thing away. And the American looks at his pint of beer and the little fly is swimming around in the froth and he's looking at it and he takes a breath and he blows it off and he says, "Yeah, that's it. The beer will be okay now." And they look round at the Scotsman and they see what he's doing. And he looks at this little fly and it's swimming around on the top of his beer. And he picks the fly up and he turns it upside down and he starts squeezing it and he says, "Spit it out, you little bugger." Kathy, you liked that. Lyra, you liked that. Skylar liked it as well. Oh, good. Kathy, you should like that one. Your Scottish heritage should understand that people in Scotland like drinking. Right. Do you want another joke? I think we need one more, right? We're finished this and I want your brain just to have a chance to me as well, to mellow out, and we're going to start a totally new topic in a few minutes. Scotland and beer. There's quite a lot of jokes about Scotland and beer. Okay. This Scottish guy goes into a bar in America at the same time, 1 o'clock every day. And he goes over to the bar and he orders 3 pints of beer and he takes them over to a table at the side and he sits on his own and he drinks them and then he leaves. And he does this every day at 1 o'clock sharp. No changes, same pattern. So he comes in the next day at 1 o'clock and the barman says, "Look, I don't want to be nosy, but I notice that you always buy 3 pints of beer. It's always 1 o'clock. You drink them and then you leave." He says, "What's going on?" And the guy says, "Oh, it's a family tradition." He said, "Me and my 2 brothers, when we lived in Scotland, we used to meet up at 1 o'clock every day. We'd go to a pub at 1. We'd get a pint of beer and we'd drink it, and it was a way of, being together. But we've all emigrated all over the world now. We're in different places, so you keep the tradition going. Wherever we are in the world, at 1 o'clock, we go into a bar and we get 3 pints of beer." And the barman says, "Oh, that kind of makes sense now." Okay. And he gets his pints and he drinks them and he leaves. And the next day, the Scots guy goes up to the bar and he says, 2 pints of beer. He gets them and he goes and he sits down and the barman's saying, "Oh God, something terrible's happened. There's only 2 pints. And he goes over and he says to the guy, says, "I noticed you only bought 2 pints of beer today instead of 3. And is there anything wrong?" And Scotsman said, No. He says, "There's nothing wrong." He says, "I've just decided to give up drinking." Oh, come on, Ryan. Let that one sink in. Oh, God, Ben Rose is crying. I think that's that bad. Sorry about that, Ben. Okay, I think we are suitably, what's the word, punished. So I would like to start our next section and see how much we can get done in the time that we've got. In our next section, not surprisingly, is section 6.2. And its full title is Volumes of Revolution. So we're going to find out that you can actually use integrals, integration, to find the volume of some shapes. So let's show you how it works. And there's different versions of it, but we're going to start off obviously with the more straightforward and then get uglier. Suppose I have a function y equals f of x, and it starts at a and it finishes at b. And now it gets a little bit harder to imagine, but I want you to try and imagine that the x-axis had this shape rotated round. So this curve is going to be rotated round the x-axis. Now, if you did that, can you imagine that the shape that you would get would look like a bell? And that's called a volume of revolution. It's the shape, the volume shape that you get if you take a curve and you rotate it about the x-axis. And we are going to find the volume of that bell shape or any shape that you would care to imagine, right? So what's the formula? Because it is basically a formula. V, the volume, is the integral from a to b of pi radius squared dx. Now you might say, what is this radius? Well, what you got to imagine doing is picking a random point between here and here. And can you imagine you had your little rectangle going like this? If you took this rectangle and rotated it about the x-axis, wouldn't you get a little shape that looked like that? A little disc. It's called a disc. And the radius, in this case, is the distance from the x-axis to the curve. That's the radius. So it's the integral from a to b pi, the function, squared. Now, the reason I didn't just jump in and tell you this formula is that this idea of pi radius squared is going to help us do more complicated situations later on, right? So I want you to think of radius as just being, in this case, the height of the function. So we're going to start off with single functions rotated about the x-axis, and this is the formula that's going to make that happen. Let me try a function. Suppose we take the square root of x from 0 to 4, which is basically that shape there, right? And we rotate it about the x-axis. So can you imagine what the shape might look like? It would look probably something like this. Wouldn't it look like an acorn on its side? Can you imagine? That would be the x-axis popping out. That's what I see, right? We're going to find the volume of that acorn. It's the integral from start to finish, pi, the function, squared, dx. I typically take the pi out and do this fella. The pi just gets in the way of the calculations, and I'm allowed to do that. Right, that's going to be the integral from 0 to 4 of the square root of x squared Oh, isn't that pretty? If you take the square root of x, which is what that function is, but you square it, don't you just get x? And that becomes 1/2 x squared evaluated at x equals 0 to x equals 4. And if you plug in 4, you get 1/2 times 4 squared, take away a whole load of nothings. And that's 8, and 8 in pi get you the answer 8 pi. Volume of revolution questions almost always have a pi at the end. They end up being 8 pi, 3/4 pi, 17/99 pi. And can you imagine the reason why they always have a pi is because isn't that pi going to be tagged on at the end of the number? Right. Is that kind of cool? Actually, in a lot of ways, at least this question, isn't it a lot quicker and easier than that horrible thing I only did about a third of? You know, it's going to take you about half an hour to do that last question, you know, the area on between two curves question. So this is much cleaner. Let's try another one. Suppose I have the curve y equals x squared plus 2. And I want to rotate it from -1 to +1. And I want to rotate it about the x-axis. So that's basically the shape. Now, if you try to draw that shape, and I'm not going to make any do you know one of those little toys that you have string with and they throw them up in the air and they catch them and they spin them? I don't know what else to describe it as. That's what that volume of revolution looks like. Do you get a kind of visual picture of what the 3D shape might look like? Right? You don't really need to know what it looks like to get the answer right because it's all done by math, but it's kind of nice to know. Now, in this question, won't you go from -1 to 1? Can I just stick the pi out there right at the beginning so that's one less thing I need to write? The radius, which is in this case the function. So it's going to be pi, the integral from -1 to 1, of x squared plus 2 squared. Okay, how am I going to tackle this integral?
We FOIL.
I would do that. Can you trust me that that's what you eventually get? But you can check it yourself later, right? You do an x squared plus 2 times an x squared plus 2 and you FOIL it, right? Now, in this case, it's going to be power rule, in 4x, evaluated at -1 and at 1. Okay, if you plug 1 in here, you're going to get a fifth. You plug 1 in here, you're going to get 4/3. You plug 1 here, you're going to get 4. If you plug in -1 here, you're going to get -1/5. You plug it in here, you're going to get -4/3. And you plug it in here, you're going to get -4. And you can take this guy and subtract all of those, or you can find these separate and then subtract them. It really doesn't matter. Would you agree you're going to get an ugly fraction when you're finished, no matter what you do? So I am going to try and do this as one big ugly calculation, and I'm going to use the calculator, the TI-84, if I can make this thing appear. And it'll be able to show you how you could do quite messy, big, ugly fraction calculators. Right, here's my guy. I'm not putting the pi in, that gets stuck on at the end, but I'm going to go a bracket. 1/5, add 4/3, add 4. Close the bracket. Take away, start a bracket, negative 1/5, subtract 4/3, subtract 4, close the brackets. Now, very careful here. Have you noticed that that guy there is smaller than everybody else? And that's because that is for 1/5. And all the other things, subtractions. And you see, if you put a negative when it should be a subtraction, or a subtraction where it should be a negative, and they look very similar. Look, subtraction, negative, right? If you mix them up, the answer will probably say error, and you'll scratch your head and wonder why. Now, when I hit enter in this in a few seconds, we are going to probably see an ugly decimal. And then hit math button, choice number 1, which is fraction, and boom. It's 166/15 pi. Now, would you agree that was a lot easier to do than me going back, and I'll return now back to the question, and trying to do all the steps myself? Because trying to do all that in my head, or whatever other way, take away trying to do all that in my head, aren't you likely to screw up? But as long as you type it into the calculator, aren't you going to get the correct answer as long as you type it in right? And notice a little pi at the end. Cool. Now, I'm going to pick a question now that proves that this works. And you might say, well, how can you prove that this works? Isn't x squared plus y squared equals 9 a circle of radius 3, centre of the origin? Can you remember that? So that's a circle, or meant to be a circle, and the radius is 3. So won't its area, won't this thing, if you rotate this thing about the x-axis, won't this thing create a sphere? Right, a ball. Do you know, does anybody know what the formula for the equation of a sphere is? 4/3 pi r
Cube.
cubed. So in this question, 4/3 pi 3 cubed. The answer is 36 pi. So I found the answer to what this would be if you rotated it about the x-axis, and the answer is 36 pi, and I know it's 36 pi because this is the formula for getting the volume of a sphere of radius r, and if r is 3, you plug 3 in and that's the answer, right? So back to this question then. How do I make this happen? Well, I have to do a bit of work. And I am only going to take the top half of the shape from -3 to 3, and this curve is called the square root of 9 minus x squared. Technically, it should be plus or minus, but if you only take the top half, right, it's a plus. And I'm going to rotate this shape about the x-axis, and wouldn't this generate the sphere? So if I end up getting this answer, right, this guy here, rotated about the x-axis, if it ends up being 36 pi, isn't that kind of proof that this method works? Because it gets the same answer. So it's going to have a volume from -3 to 3, stick out the pi, the function squared. -3 to 3, this guy, squared. -3 to 3, that guy. See, if you square a square root, don't they essentially cancel out and you get a nice answer? In this case, 9 minus x squared. I can then power roll. Nine lots of 3, take away 1 3 cubes, minus 9 lots of negative 3, take away that guy. And I could actually, I'm not wanting to because it's too much jumping around, but can you imagine I did this calculation on this fella? Oh, actually, I can do it on this fella, and we'll see what we get. Brackets, 9 times 3, take away, put in brackets, 1/3 times 3 cubed, close the brackets. Subtract 9 times negative 3, subtract 1/3 times negative 3 cubed, close brackets, 36. Bingo. We have just found the volume of that sphere. Now, what's kind of cool here is, well, lots of cool things. I used this formula to create the check. But if I never knew that formula, right? Nobody's invented it yet. Wouldn't I still have been able to get the answer 36 pi? Because doesn't this thing not require formula? It just requires you to know what the equation of that particular guy is. I think that's pretty impressive. And I'm going to do something even more impressive, I think. I am going to do creating this formula. It's probably the first time that we've ever, in your math career, got you to find out what a formula is. So imagine you're the first person in the universe who is going to tackle the question, what is the formula for the volume of a sphere of radius r? And you might think, where in heck did this come from? Well, I'm going to show you how it would be done. I'm going to start with a circle. And the circle is x squared plus y squared equals r squared. Isn't that the general version of every circle in the universe whose radius is r? And won't this circle, won't that be negative 3 and won't that be plus 3? Sorry, negative r and plus r. It used to be negative 3 and plus 3 in the equation we've got. Would you agree? And if I rearrange this, won't y be the square root of that guy? And I want you to think of r as just a constant here, right? An unknown number. So I'm going to take the top half from negative r to r. I'm going to rotate it in the x-axis. And if I do that, won't I make a sphere with a radius of r? So I'm going to find the volume of this shape. Everything we need is already set up. It's the integral from negative r to r, stick a pi on the outside, the function squared. Negative r to r, the function squared dx. Negative r to r of this guy. Now, it's a little bit trickier than expected. Hopefully we can do it. R squared is a constant, right? It's like 52 squared or 3 squared. It's just a number. If you find the antiderivative of a number, don't you just get the number with an x attached? So the antiderivative of r squared is r squared x. The antiderivative of This guy is just a power rule. And I'm going to evaluate it from x equals negative r to r. So it's going to be r squared times r, take away 1/3 r cubed, minus r squared times negative r, take away negative 1/3 negative r cubed. Right, r squared times r is r cubed, take away 1/3 r cubed. This guy times this guy is negative r cubed. This guy is negative r cubed. Two negatives make a plus. I get that fella. I have an r cubed. I take away a third r cubed. Take away a negative is add an r cubed. Take away that guy. We have this. 2 pi, take away 2/3. So 2r cubed, take away 2/3. And that guy is 4/3 r cubed. The volume of a sphere using calculus. Before calculus was invented, they didn't know how to get the exact value, I guess, for the volume of a sphere. Would you agree? If you don't have a formula, how can you do it, right? Now, they had numerical techniques that are good at getting you pretty close, but that's not pretty close. Isn't that perfect? I think that's pretty amazing that we now have the ability to find the volume of rotated shapes, right? Things where they rotate the shape right about the x-axis. It's pretty cool. Now, next thing I'm going to do is a side issue. I'm going to show you how to integrate sine squared. And how to integrate sine squared is kind of useful because you can imagine that you might get a question where sine x is rotated about the x-axis. So won't you have to integrate sine squared, for example? To be able to do that, you have to know what sine squared x is written as in terms of a different expression. And it's more trig identities. Oops. Let me just do that again because I don't want this to be a mess. Sine squared x is 1/2 1 minus the cosine of 2x. And you can go and look up your trig notes, but somewhere or other, that should have been written down once in your life. Which means this now becomes 1/2 1 minus the cosine of 2x dx, which means that becomes this. Okay, this has happened quite a few times today. I'm going to integrate this, right? And I'm going to have to separate it into two integrals. That guy is dead easy. Right, it's a 1/2 x. But I just did it to get him out of the way. Here we go. I think the 4th time today I've had to ask this, so hopefully it's going to be really quick. What technique do you think I'm going to use to integrate the cosine of 2x?
U sub?
Come on, don't leave me hanging here. Yes, and who is the U sub going to be?
2x.
2x. I know it's a baby question, but I just want to hear you say it, right? Are you getting comfortable now that you can do sines of 2x and cosines of 4x and who knows what else? Secant squared of 7x and tan of 9x, right? 2x does the job. You differentiate with respect to x. You do the crossover and you isolate. So this is going to be the takeaway, the integral of 1/2 cosine of 2x becomes cosine of u, and 1/2 du. So it's 1/2 take away 1/4 cosine of u du. If you integrate a cosine, you get a sine. And make sure everybody gets converted. So we now have a new guy. And if I think that I might want to use that new guy because he might appear in a question somewhere, can I go to my little list and write down sine squared x is 1/2 x, take away 1/4 the sine of 2x, add c, which means the next time I need to integrate sine squared x, can't I just write that down instead of having to do all of this all over from scratch? You like?
That's nice.
It is nice. So I'm going to give you a puzzle here. If sometimes you're going to find sine squared, couldn't you just also sometimes going to have to find cos squared? Right. And here's the puzzle. You're going to go through a whole process that looks just like this, right? Yeah. You're going to have to find what cos squared is in terms of this guy, and it does exist. But I want you to try and imagine what you think the answer is based on what this answer is. So it's basically a guess stroke pattern. To me, there's probably two likely candidates. Couldn't that maybe be a cosine 2x? That might happen. Or couldn't that maybe be a plus? Any guesses? So I don't have to, so we don't need to do this. What's your gut feeling? You think that's going to turn into a plus, or do you think it's going to look the same, but a cosine of 2x?
Plus sign.
And you're allowed to, I like your guessing. It's going to be a plus. So you can go over here and you can write down what the cos squared is. So if you come across a question, oh, remember we did the tan? When you come across a question and you finally get the answer and you don't want to have to do that again, can't you just go to your little table and add it? And I've just done the sine squared, and if you do the working, you can do the cos squared. So why am I doing that? Because I want to be able to find a volume of revolution of this fella. Now, if you did this guy, it would look to me like a lemon, right? Maybe it looks more curved than I wanted it to, but that shape would look to me like a lemon, right? That's the volume would look like. And the x-axis would be popping out here. So let's find the volume. Pi, the integral from start to finish, of f of x squared dx. Now, if you take sine x and you square it, don't you call it sine squared x? Right, sine x times itself is called sine squared x. And since we've spent some time making our life easy, won't that be pi 1/2 x take away 1/4 sine 2x evaluated at 0 to pi? Because we already know what he is, right? That now becomes 1/2 pi take away 1/4 the sine. 2 times pi gets you 2 pi. Subtract. 1/2 0 is 0, and isn't the sine of 0 0? So isn't that just a whole load of zeros? And I have a pi, and I have a 1/2 pi. What is the sine of 2 pi? What number is the sine of 2 pi?
Is that 90?
Well, it's a sine, so when you do the sine of an angle, you get numbers somewhere between -1 and 1. So if you
That's
sketch
0.
the sine
It's just 0.
at 2 pi, what would you get? Yes, you'd get 0. Which means that the volume of this shape is a 1/2 pi squared. I think if you try to guess that answer, you'd probably have to guess an awful lot of times, and you might still never guess it right. Would you agree it's not that obvious that the volume of this lemon shape, right, what you get when you take a sine x rotated about the x-axis, would be a 1/2 pi squared? But it is. You agree? I could do cos squared. I could do, anything you possibly could think of. Let's show you a weird one, still with sine. Because we haven't seen what happens to this. Oh, darn it. Some of the shape is below the x-axis and some of it's above, and you're going to rotate this thing. Now, if you imagine what that looked like, can you imagine two identical lemons meeting up? It would look like a very, very small necklace made out of two lemon-shaped pearls, right? The volume of that shape is the integral from 0 to pi, 0 to 2 pi, of f of x squared. So the good news is, you don't care if the curve is below the x-axis, you don't care if the curve is above the x-axis. The formula takes care of it. So you don't need to break it into two pieces and find each one and add them up. You don't need to figure out who's high and who's low. None of that matters. That's matters. Which means that we're essentially going to be doing this guy. And the only real difference is that we start at 0 and we finish at 2 pi. Now, isn't that nice that this particular technique is so versatile that you don't need to tweak it when things end up below the x-axis or something like that happens? Now let's continue this one and see what we get then. It's a 1/2 times 2 pi, take away 1/4 the sine of 4 pi, minus 1/2 times nothing is nothing, and that's nothing, so a whole load of nothings. What's the sine of 4 pi? I don't want to wait as long as the last time. Sine of 4 pi.
Isn't that
Come
the
on.
same thing as 2 pi, 0?
Yeah, it's still 0. Correct, you're right. So what do I get? A half times that is pi. Take away 0. Whoa. The volume of this little shape here, right, with the x-axis going through the center of it. That's a very elegant answer, isn't it? That its volume is pi squared. And then you think about it, it kind of makes sense. Didn't we just find that guy? And it was a half pi squared. Wouldn't that guy be the same thing if you rotated it about the x-axis? Wouldn't you still get a shape that looks exactly the same lemon? And wouldn't it have the same, a half pi squared? So together, shouldn't that be 1 pi squared, which is?